Okay, what I'm going to go over now is what's called KSP, or solubility product, and the solubility of slightly soluble compounds. First, the way compounds get dissolved in water, it's kind of a simplification, but let's first remember that water is a polar molecule. It is a bent molecule where the the oxygen is up on this end and it has a slightly negative charge, and the two hydrogens are kind of down here at an angle, and each one of these hydrogens has a slightly positive charge. That makes the molecule overall being polar, because down here I have one end that's slightly positive and another end that's slightly negative. Okay, now let's think of an ionic solid as being repeating cations and anions in a big crystal. Okay, so the positively charged circles are the cations, the negatively charged circles are the anions. Okay, and then this is water. All that stuff up there is water. And water being a polar molecule, the slightly negative head of water will be attracted to the positively charged ions, the cations, in my crystal lattice, and they'll tend to orient themselves towards the cation, with the slightly negatively charged oxygen pointing at it. And the attraction between all of these, and there'll be a lot more than just two water molecules, the attraction between all of these water molecules with the slightly negative oxygen on the positively charged ion here, the cation, will have a tendency to pull it out. The attraction between the water and this may end up being stronger than the attraction between the cation and these anions that are right near it. And if they are able to pull it out, it'll pull out here with what's called a hydration sphere of water molecules. The first layer of water molecules right around the ion will be oriented like this. And here it is out away from the crystal lattice, floating around in the rest of the water. Obviously, this is not drawn to scale, but you guys get the idea. The negatively charged ions, the anions, will have the water molecules naturally attracted with the slightly positively charged hydrogens, and they will surround it and pull on it because of the attraction between the negative and the slightly positive here. And if there's enough water molecules around this, if the attraction between the water molecules and that anion is greater than the attraction between the anion and these cations, the anion will get pulled out and will end up being floating around in the water, within the immediate first layer of water right around it will be water molecules oriented like this, and that's called a hydration sphere. And that tends to keep these ions out, floating about on their own. Okay? And so if we take a solid like zinc iodate, which, oh, by the way, I meant to go back. If water is able to completely pull apart all of the ions, then when I'm done, I'll have none of this solid here left visible in the container. Will all be dissolved into these separate ions floating around in solution. And that's what it means. Like if you put a little bit of sodium chloride in the water's going to surround it and pull all the ions out until all the ions are floating around with a little hydration sphere around them, and there's no more salt crystals, table salt, sodium chloride, left in here, right? They're all pulled out and floating around, and that's why we say sodium chloride is soluble in water. If I have something that's far less soluble in water, like zinc iodate, some of the zinc ions and some of the iodate ions will get pulled out and will be floating around, but most of them won't. And then I'll end up with an equilibrium between the ones that are dissolved and the ones that aren't dissolved. And what will happen is, imagine this is the zinc and this is one of the iodates. I'll end up with an equilibrium where sometimes the zinc comes back down and gets stuck here back in the crystal lattice, but then another zinc gets pulled out by the water. So I've got the rate of, I guess you'd call it deposition, the rate of the zinc depositing back into the crystal lattice, and the rate of another zinc being pulled out, then the rate of the iodate being deposited back, and the rate of another iodate being pulled back out. If the rate of it being pulled apart is equal to the rate of other ones depositing back in, then we would say that's equilibrium, okay? And there's an equilibrium set up between the solid and the ions, okay? And we can set up an equilibrium equation for that. It's called KSP for solubility product. And that's going to be the zinc concentration times the iodate concentration squared. Because remember, we have AA plus BB is in equilibrium with CC plus DD. And K for that would be C to the C, D to the D, A to the A, and B to the B. Well, it's the same thing that's going on here. And the value for this is in your book. It's in the appendix in your book. That happens to be 3.9 times 10 to the minus 6. Okay? So now we're going to do some calculations. And we're going to see how much zinc will dissolve if I throw some solid zinc iodate into pure water. So let me erase this. So if I put some solid zinc iodate into pure water, I'm going to have this ZnIO3 solid is in equilibrium with Zn2 plus aqueous plus 2 iodate aqueous, and I can set up an ice chart. ICE. Now, pure solids and pure liquids are not factored into the equilibrium constant. And when I put this in pure water, the initial concentration of this is 0, and the initial concentration of that is 0. Okay? Now, when we do an ice chart like this, we would expect to put plus X and plus 2X. But for whatever reason, the kind of the tradition or the custom is instead of using X, they use a capital letter S. Exact same mechanics. So this is going to go up by S. And if this is S and that's a 2, this will go up by 2S. So at equilibrium, the concentration will be 0 plus S, which is S. The concentration of the iodate will be 0 plus 2S, which will be 2S. Okay? Now I'm going to erase some stuff because I need some room. But I'm going to end up with KSP equals 3.9 times 10 to the minus 6. That's going to be equal to the zinc concentration at equilibrium, which is S, times the iodate concentration squared. That's going to be 2S squared. Right? Because at equilibrium it's 2S. Don't forget you have to square it. Here's where you have to be careful. 2 squared is 4, right? Then I'm going to have S squared times S. That's going to be 4S cubed. So now we're going to solve for S. S will be equal to 3.9 times 10 to the minus 6 over 4 and I want the cube root, or to the 1/3 power. 3.9 times 10 to the -6 divided by 4. And then, let's see here if I can do it in my calculator right. And I get, if I did it in my calculator right, I get S equals 0.00992. Okay, that looks right. Hope I did it right. Well, what does this mean? This means that at equilibrium, the concentration of the zinc ion is going to be 0.00992 molarity. And the concentration of the iodate ion, I know there's a 2 here. Don't put a 2 in front of this. This is the chemical name. That's going to be twice that. So 0.00992 times 2 is going to give me 0.0198 molarity. But more important, well, not more importantly, but also importantly, for every one of these that's formed, one of these dissolves. See the one here and the one there, right? So the S also is the molar solubility of zinc iodate is equal to 0.00992 molar. That means if I took a big handful of zinc iodate and I threw it into a big container of water, that means I would have 0.00992 moles of the solid zinc iodate dissolve into each liter of water. And that's called the molar solubility. Okay? Where you have to be careful of is this part right here, the 2s squared, right? Because I got that it's 2s and then it's squared, so it's 2s squared. You have to make sure you square the 2 to get a 4. And don't forget, s times s squared is going to be 4s cubed. But you have to take the cube root properly, and I sure hope I did it in my calculator right. Okay, so let's see, 3.9 times 10 to the -6 divided by 4, and then y to the 1/3 power. Yeah, 0.0991, right? 0.0992. Okay. Now, let's erase this stuff. What is the molar solubility? Let's do this. The molar solubility of zinc iodate in a 0.1 molar zinc chloride solution. Okay, and I tend to write going up to the side, but okay, well, this right here is the molar solubility of zinc iodate in pure water. But what about in a 0.1 molar zinc chloride solution? Okay, zinc chloride is a completely soluble salt. From the solubility chart that you were given in Chem 1A, all chlorides are soluble except for silver, mercury, and lead. So zinc chloride, well, it's going to go one way. Let me rephrase that. aqueous, if it's 0.1 molar zinc chloride, that's code talk, that's Cl2. That's code talk for Zn2 plus aqueous plus 2Cl minus aqueous. When I initially put it in there, that's going to completely break apart. And when I'm done, I'm going to have none of it left. Beginning and end. I'm going to have none of this to start with and none of that to start with. But when I'm done, for every one of these, I get one of these. So it'll be 0.1 molar. And for every one of these, I get two of these. So this will be 0.2 molar. So when it says 0.1 molar zinc chloride solution, first thing my mind jumps to is that means I'm going to get 0.1 molar zinc for starters. So this is going to be 0.1 molar zinc ion before I've even thrown in the zinc iodate. Now, the chloride ion is a spectator ion, and it's not part of this chemical reaction here, so I can ignore it. Okay? It's not gonna shift my equilibrium. But what will happen if I have some zinc in my solution already from zinc chloride? This extra zinc is going to tend to push the equilibrium back this way. The zinc iodate, not as much of the zinc iodate will dissolve because I already have some zinc in solution from the zinc chloride taking up the places where the zinc from the zinc iodate would occupy if it dissolved. Okay? So I have some zinc there already, and I have no iodate in there because I said it was 0.1 molar zinc chloride. Now, when I throw in the zinc iodate, this is going to go up by S. This is going to go up by 2S. So when I'm done, I'm going to have 0.1 plus S. In here, I'm going to have 2S. Okay, I'm going to erase this. I need this space. So my KSP is 3.9 times 10 to the minus, what did I say, minus 6? That's going to be equal to zinc 2 plus, Cl minus, excuse me, not Cl minus, IO3 minus squared. Don't put a number 2 in there. See that number 2? Don't put the 2 in there. Goes up here. That number 2 is not a part of the chemical identity. That's going to be equal to 0.1 plus S times 2S squared. Well, solving for S, this could be a difficult problem because I'm going to end up with 0.1 plus S, and then I'm going to end up with 4S squared, right? When I square that, I'm going to end up with a cubic problem, right, to solve for S. It's going to be tough. But 3.9 times 10 to the minus 6 means typically my S is going to be a very small number because this means it doesn't like to dissolve very much. And if it doesn't like to dissolve very much, you're not going to get very much S, right? So if that means it's a small number, I'm willing to bet you that I can use the S is small approximation, where 0.1 plus S is going to be really close to just 0.1. So in that case, I'm going to end up with 3.9 times 10 to the minus 6 will be equal to 0.1 times 4S squared. Then when I solve for S, I'm going to have here 3.9 times 10 to the minus 6 divided by 4 and 0.1 square root of all that. So 3.9 times 10 to the minus 6 divided by 4 divided by 0.1. Take the square root of that, and I'm going to get 0.0030. What does that mean? Well, we said at equilibrium, let me erase this. We said that if you back up a little bit, as equilibrium, concentration of zinc 2 plus at equilibrium was equal to 0.1 plus S, and it's going to be 0.1 plus 0.003, which is going to be really close to 0.1 molar, right? And the concentration of the iodate ion was equal to 2S, and that's going to be equal to 0.0060 molarity. But also, remember, for every one of these that dissolves, one of these units dissolves, and that means the molar solubility of the zinc IO3 2 solid in a 0.1 molar zinc chloride solution is 0.0030 molarity. And that is lower than that. I mean, it's about 3 times lower, right? 0.003 is about 3 times smaller than 0.0092, 3.5. Let's see. 0.00992 divided by 0.003. Yeah, it's 3.3 times smaller, which makes sense. If I dissolve this in water, I'm going to have all kinds of space for the zinc and the iodate to dissolve into the water. But if I try and dissolve this in a solution that already has zinc floating around in it, not as much as this is going to be able to dissolve, because the space that zinc was going to go into, the zinc from this, is already occupied by some zinc from this. So not as much of this will be able to dissolve. Okay? And so its molar solubility is less. Okay? That's kind of how you do molar solubility problems. If you have any questions, you email me or come to office hours. Be happy to help you work on them. But you got to do a lot of these too. Okay? I guess that's it for now.